In mathematics, the Fibonacci numbers or Fibonacci sequence are numbers in the following integer sequence, or A45. By definition, the first two numbers in the Fibonacci sequence are either 1 and 1, or 0 and 1, depending on the chosen starting point of the sequence, and each subsequent number is the sum of the previous two. In mathematical terms, the sequence Fn of Fibonacci numbers is defined by the recurrence relation with seed values, or the Fibonacci sequence is named after Italian mathematician Fibonacci. His 1202 book Liber Abaci introduced the sequence to Western European mathematics, although the sequence had been described earlier in Indian mathematics. By modern convention, the sequence begins either with f0 equals 0 or with f1 equals 1. The Liber Abaci began the sequence with f1 equals 1. Fibonacci numbers are closely related to Lucas numbers in that they form a complementary pair of Lucas sequences, and they are intimately connected with the golden ratio. For example, the closest rational approximations to the ratio are 2/1, 3/2, 5/3, 8/5. Fibonacci numbers appear unexpectedly often in mathematics, so much so that there is an entire journal dedicated to their study, the Fibonacci Quarterly. Applications of Fibonacci numbers include computer algorithms such as the Fibonacci search technique and the Fibonacci heap data structure, and graphs called Fibonacci cubes used for interconnecting parallel and distributed systems. They also appear in biological settings, such as branching in trees, phyllotaxis, the fruit sprouts of a pineapple, the flowering of an artichoke, an uncurling fern, and the arrangement of a pine cone's bracts. Origins. The Fibonacci sequence appears in Indian mathematics, in connection with Sanskrit prosody. In the Sanskrit tradition of prosody, there was interest in enumerating all patterns of long syllables that are 2 units of duration, and short syllables that are 1 unit of duration. Counting the different patterns of L and S of a given duration results in the Fibonacci numbers. The number of patterns that are m short syllables long is the Fibonacci number fm plus 1. Susan Thagunachalake writes that the development of the Fibonacci sequence is attributed in part to Pingala, later being associated with Virahankar, Gopala, and Hemachandra. Parmanand Singh cites Pingala's cryptic formula Masrauchar and cites scholars who interpret it in context as saying that the cases for m beats is obtained by adding a s to fm cases and l to the fm-1 cases. He dates Pingala before 450 BC. However, the clearest exposition of the sequence arises in the work of Virahankar, whose own work is lost, but is available in a quotation by Gopala. Variations of 2 earlier meters is the variation. For example, 4, a meter of length, 4 variations of meters of 2 and 3 being mixed, 5 happens. Works out examples 8, 13, 21. In this way, the process should be followed in all Matra Vrtas prosodic combinations. The sequence is also discussed by Gopala and by the Jain scholar Hemachandra. Outside of India, the Fibonacci sequence first appears in the book Liber Abaci by Leonardo of Pisa, known as Fibonacci. Fibonacci considers the growth of an idealized rabbit population, assuming that a newly born pair of rabbits, one male, one female, are put in a field. Rabbits are able to mate at the age of 1 month so that at the end of its 2nd month a female can produce another pair of rabbits. Rabbits never die and a mating pair always produces 1 new pair every month from the 2nd month on. The puzzle that Fibonacci posed was, how many pairs will there be in 1 year? At the end of the 1st month, they mate, but there is still only 1 pair. At the end of the 2nd month, the female produces a new pair, so now there are 2 pairs of rabbits in the field. At the end of the 3rd month, the original female produces a 2nd pair, making 3 pairs in all in the field. At the end of the fourth month, the original female has produced yet another new pair. The female born 2 months ago produces her first pair also, making 5 pairs. At the end of the nth month, the number of pairs of rabbits is equal to the number of new pairs plus the number of pairs alive last month. This is the nth Fibonacci number. The name Fibonacci sequence was first used by the 19th century number theorist Edouard Lucas. List of Fibonacci numbers. The first 21 Fibonacci numbers Fn for n equals 0, 1, 2, 20 are. The sequence can also be extended to negative index n using the rearranged recurrence relation, which yields the sequence of neg-Fibonacci numbers, satisfying thus the bidirectional sequences used in mathematics. The Fibonacci numbers occur in the sums of Shallow diagonals in Pascal's triangle. These numbers also give the solution to certain enumerative problems. The most common such problem is that of counting the number of compositions of 1s and 2s that sum to a given total n. There are fn plus 1 ways to do this. For example, if n equals 5, then fn plus 1 equals f6 equals 8 counts the 8 compositions. 1 plus 1 plus 1 plus 1 plus 1 equals 1 plus 1 plus 1 plus 2 equals 1 plus 1 plus 2 plus 1 equals 1 plus 2 plus 1 plus 1 equals 2 plus 1 plus 1 plus 1 equals 2 plus 2 plus 1 equals 2 plus 1 plus 2 equals 1 plus 2 plus 2, all of which sum to n equals 5 equals 6 minus 1. The Fibonacci numbers can be found in different ways among the set of binary strings, or equivalently, among the subsets of a given set. The number of binary strings of length n without consecutive 1s is the Fibonacci number fn plus 2. For example, out of the 16 binary strings of length 4, there are f6 equals 8 without consecutive 1s. They are 0000, 0001, 0010, 0100, 0101, 1000, 1001 and 1010. By symmetry, the number of strings of length n without consecutive 0s is also fn plus 2. Equivalently, fn plus 2 is the number of subsets s1, n, without consecutive integers. I plus 1, s for every I. The symmetric statement is, fn plus 2 is the number of subsets s1, n, without 2 consecutive skipped integers. That is, s equals a1 less than DAC, with I plus 1 I plus 2. The number of binary strings of length n without an odd number of consecutive 1s is the Fibonacci number fn plus 1. For example, out of the 16 binary strings of length 4, there are f5 equals 5 without an odd number of consecutive 1s. They are 0000, 0011, 0110, 1100, 1111. Equivalently, the number of subsets s1, n, without an odd number of consecutive integers is fn plus 1. The number of binary strings of length n without an even number of consecutive 0s or 1s is 2fn. For example, out of the 16 binary strings of length 4, there are 2f4 equals 6 without an even number of consecutive 0s or 1s. They are 0001, 0111, 0101, 1000, 1010, 1110. There is an equivalent statement about subsets. Relation to the golden ratio. Closed form expression like every sequence defined by a linear recurrence with constant coefficients. The Fibonacci numbers have a closed form solution. It has become known as Binet's formula, even though it was already known by Abraham de Moivre, whereas the golden ratio A001622, and since this formula can also be written as to see this. Note that phi and psi are both solutions of the equations, so the powers of phi and psi satisfy the Fibonacci recursion. In other words, and it follows that for any values a and b, the sequence defined by satisfies the same recurrence if a and b are chosen so that u0 equals 0 and u1 equals 1, then the resulting sequence un must be the Fibonacci sequence. This is the same as requiring A and B satisfy the system of equations, which has solution producing the required formula. Through algebraic manipulation, the equation can be rewritten to form a solution for any sequence computation by rounding, since for all n0, the number fn is the closest integer to. Therefore, it can be found by rounding, that is by the use of the nearest integer function, or in terms of the floor function. Similarly, if we already know that the number f greater than 1 is a Fibonacci number, we can determine its index within the sequence by limit of consecutive quotients. Johannes Kepler observed that the ratio of consecutive Fibonacci numbers converges. He wrote that, as 5 is to 8 so is 8 to 13, practically, and as 8 is to 13, so is 13 to 21 almost, and concluded that the limit approaches the golden ratio. This convergence holds regardless of the starting values, excluding 0. This can be derived from Binet's formula. For example, the initial values 3 and 2 generate the sequence 3, 2, 5, 7, 12, 19, 31, 50, 81, 131, 212, 343, 555, etc. The ratio of consecutive terms in this sequence shows the same convergence towards the golden ratio. Another consequence is that the limit of the ratio of two Fibonacci numbers offset by a particular finite deviation in index corresponds to the golden ratio raised by that deviation, or, in other words, decomposition of powers of the golden ratio. Since the golden ratio satisfies the equation, this expression can be used to decompose higher powers as a linear function of lower powers, which in turn can be decomposed all the way down to a linear combination of and 1. The resulting recurrence relationships yield Fibonacci numbers as the linear coefficients. This equation can be proved by induction on n. This expression is also true for n less than 1 if the Fibonacci sequence Fn is extended to negative integers using the Fibonacci rule matrix form, a two-dimensional system of linear difference equations that describes the Fibonacci sequences, which yields as the eigenvalues of the matrix A are and for the respective eigenvectors n and the initial value. The nth term is from which the nth element in the Fibonacci series as an analytic function of n is now read off directly. Equivalently, the same computation is performed by diagonalization of A through use of its eigendecomposition, where n, the closed-form expression for the nth element in the Fibonacci series, is therefore given, by which again yields the matrix A has a determinant of -1, and thus it is a 2 times 2 unimodular matrix. This property can be understood in terms of the continued fraction representation for the golden ratio. The Fibonacci numbers occur as the ratio of successive convergence of the continued fraction for phi, and the matrix formed from successive convergence of any continued fraction has a determinant of +1 or -1. The matrix representation gives the following closed expression for the Fibonacci numbers. Taking the determinant of both sides of this equation yields Cassini's identity. Moreover, since an m equals n plus m for any square matrix A, the following identities can be derived, in particular, with m equals n. These last two identities provide a way to compute Fibonacci numbers recursively in O arithmetic operations and in time O log, where m is the time for the multiplication of two numbers of n digits. This matches the time for computing the nth Fibonacci number from the closed-form matrix formula, but with fewer redundant steps if one avoids recomputing an already computed Fibonacci number. Recognizing Fibonacci numbers, the question may arise whether a positive integer x is a Fibonacci number. This is true if and only if one or both of or is a perfect square. This is because Binet's formula above can be rearranged to give, which allows one to find the position in the sequence of a given Fibonacci number. This formula must return an integer for all n, so the radical expression must be an integer. Combinatorial identities. Most identities involving Fibonacci numbers can be proved using combinatorial arguments, using the fact that Fn can be interpreted as the number of sequences of 1s and 2s that sum to n-1. This can be taken as the definition of Fn, with the convention that f0 equals 0, meaning no sum adds up to -1, and that f1 equals 1, meaning the empty sum adds up to 0. Here, the order of the summand matters. For example, 1 plus 2 and 2 plus 1 are considered two different sums. For example, the recurrence relation, or in words, the nth Fibonacci number is the sum of the previous two Fibonacci numbers, may be shown by dividing the Fn sums of 1s and 2s that add to n-1 into two non-overlapping groups. One group contains those sums whose first term is 1 and the other those sums whose first term is 2. In the first group the remaining terms add to n-2, so it has f sums, and in the second group the remaining terms add to n-3, so there are fn-2 sums. So there are a total of fn-1 plus fn-2 sums altogether, showing this is equal to Fn. Similarly, it may be shown that the sum of the first Fibonacci numbers up to the nth is equal to the nd Fibonacci number -1. In symbols, this is done by dividing the sums adding to n plus 1 in a different way, this time by the location of the first two. Specifically, the first group consists of those sums that start with 2, the second group those that start 1 plus 2, the third 1 plus 1 plus 2, and so on, until the last group, which consists of the single sum where only 1s are used. The number of sums in the first group is f in the second group, and so on, with one sum in the last group. So the total number of sums is f plus f plus 1, and therefore this quantity is equal to f. A similar argument, grouping the sums by the position of the first one rather than the first two, gives two more identities. And in words, the sum of the first Fibonacci numbers with odd index up to f2n-1 is the th Fibonacci number, and the sum of the first Fibonacci numbers with even index up to f2n is the th Fibonacci number -1. A different trick may be used to prove, or in words, the sum of the squares of the first Fibonacci numbers up to fn is the product of the nth and th Fibonacci numbers. In this case, note that Fibonacci rectangle of size fn by f can be decomposed into squares of size fn, fn-1, and so on to f1 equals 1, from which the identity follows by comparing areas. Other identities. Numerous other identities can be derived using various methods. Some of the most noteworthy are Cassini and Catalan's identities. Cassini's identity states that Catalan's identity is a generalization. Decaine's identity, where lane is the nth Lucas number. The last is an identity for doubling n. Other identities of this type are by Cassini's identity. These can be found experimentally using lattice reduction, and are useful in setting up the special number field sieve to factorize a Fibonacci number. More generally, putting k equals 2 in this formula, one gets again the formulas of the end of above section matrix form. Power series. The generating function of the Fibonacci sequence is the power series. This series is convergent for in its sum has a simple closed form. This can be proved by using the Fibonacci recurrence to expand each coefficient in the infinite sum. Solving the equation for s results in the above closed form. If x is the reciprocal of an integer k that is greater than 1, the closed form of the series becomes in particular for all positive integers m. Some math puzzle books present as curious the particular value that comes from m equals 1, which is similarly m equals 2 gives reciprocal sums. Infinite sums over reciprocal Fibonacci numbers can sometimes be evaluated in terms of theta functions. For example, we can write the sum of every odd-indexed reciprocal Fibonacci number as and the sum of squared reciprocal Fibonacci numbers as if we add 1 to each Fibonacci number in the first sum. There is also the closed form, and there is a nested sum of squared Fibonacci numbers giving the reciprocal of the golden ratio. No closed formula for the reciprocal Fibonacci constant is known, but the number has been proved irrational by Richard-André Jeanine. The Millen series gives the identity which follows from the closed form for its partial sums as n tends to infinity.